Okay, everyone, let's get started. You guys in the back, can you move up a little bit? Scooch up a little. Uh-oh. Okay, everyone have a syllabus? Okay, so welcome back. Welcome to CSCE 491. Let's run through the syllabus here, and then we'll get started. So section 1 is the catalog description. This is a new course technically, but it is more or less the same as the version of 317 that we used to teach. But we added prerequisites, so now you have to have taken 313 and 611. And we'll be using the stuff you learned in those classes this semester. We only have this room for this semester, so I will be spending about half the meeting times lecturing, the other half you guys will just be working in the lab, but we're always going to be coming here. We don't have a separate lecture room, unfortunately. For the electronic resources, as you guys know, I just use the Moodle Dropbox site, dropbox.csc.sc.edu. I don't use Blackboard, and I put all my lecture recordings on my YouTube channel. I've got all my courses on there for the past 5 or 6 years. We're going to be using software and hardware that's in this lab, but the same software is also available in the downstairs lab in 1D43 in case you need to access the CAD tools or something you could use there, but the hardware is in this lab, so you'll mostly be coming here. There are other courses taught. There are other courses taught in this lab though, so I'll be putting a schedule on once I have to ask Ryan what time the other classes are going to be meeting in here, and I'll put the times on the Moodle so you can plan ahead if you want to come here outside of class, so you don't risk coming here when there's someone else in here lecturing. Make sure that you check your university email or forward it, because I'll send announcements out on that. Usually those are like project extensions or bugs in the lab sheet or anything like that. And we're counting on you to find your own method for collaborating between you and your group. So, hopefully you guys are familiar with GitHub or Dropbox, or you have some way to do that, because on your accounts in here, you can't really do that. We don't have access control. So, either you open up your home directory or to everyone, or here, go syllabus, or it's not open to anyone. There you go. Does that make sense? So you'll be working in groups. Make sure you have a way to share files. We have a textbook, which is a good textbook, but it's kind of a placeholder. We don't really use it. I'm writing my own textbook, and I'll be putting the PDFs of those chapters on Moodle for you to get. I'm about halfway done with it. Section 5 is the course learning outcomes. So the objective in this class is, this class is supposed to serve as the culminating design experience for the computer engineering program. So you're supposed to put everything that you learned in our courses to work and build a computer system in this course. That's the idea. But I'll also be, as I said, I'll be spending about half the time lecturing and covering new material too. But this is supposed to be a hands-on design experience. Section 6 are the important dates. These are just cancellations and notable dates. So the last day to drop is August 30th. We have fall break October 19th. Last week withdrawal November 8th. Try to put all the important dates. We will have a final exam in this class, but I give it online, and I give you the whole finals week to take it. So we won't be using the date and time of the final for this class. I am your instructor, and I'm in the story building, room 2213, and I've got my email address, phone number. The teaching assistant is Angela Kalinko. She's one of my PhD students, and she's in my lab in the story building, which is room 2236. So if you need any help, please contact one of us. The grading structure, if we go to section 8, grading structure is 41% are the lab projects, and then we have 2 exams, a midterm and a final, and then we'll have quizzes on the material. The quizzes are mostly for me to see how well I'm covering the topics. I've got an approximate schedule. So this class is divided into basically just 4 main topics. I start out talking about interfacing, how hardware components talk to one another. So we cover basically protocols, communication protocols, serial communication protocols, UART, SPI, I2C, and JTAG. You might have heard of those, and you might have even used them, like on an Arduino system, but we're going to talk about how they work. And then I'm going to get into hardware description language and FPGAs. Obviously, you guys have already seen this in 3.13 and 6.11. We're going to use the same FPGA. We're going to go into a little bit more depth with that. Specifically, the objective here is to do hardware and software on the FPGA. So in 3.13, you guys just did software on the FPGA, and you did a little hardware, but you just kind of just assembled the system. And in 6.11, you did purely hardware design. We want to be able to take the soft-core processor and all the infrastructure and libraries of the Neos processor, and also be able to design a system Verilog component that sits in the hardware and then have them talk. That's something that you guys hadn't been able, you didn't get to do that in those other two classes. So we're going to try to bring everything together. And then we're going to talk about control theory, which is the topics that are also covered in other departments, like in electrical engineering 331, and in mechanical has a controls class. But basically the idea there is how you write an algorithm to control things in the physical world. And then we'll cover real-time systems, which is closely related to that. So real-time systems is the idea that the software has to be able to keep pace with the real world, with the physical world, in order to control it. And so you have to pay attention to performance and timing. So that'll be the last topic. So those are the four main topics I'll cover in lecture. Section 10 is what you need to do if you have a disability that you need support for. Section 11 says that we may update the syllabus, but I'll give you notice if we do, usually just because there's bugs or the university shuts down for a pandemic or something like that. We may need to update the syllabus, and I'll let you know. Section 12 is the grading scale. I use the same grading scale everyone else does. Section 13 is the academic honesty policy. This is a little unique for this class, and you guys probably remember from when you took 3.13 and 6.11. So it's a group-based work, and you're using really crappy CAD tools. Crappy in the sense that they're difficult to use, and they crash unexpectedly, and they don't have informative error messages, and they're horrible because they're written by engineers and not software people. So you're encouraged to help either your colleagues out with problems with the CAD tools. And in fact, a lot of times groups solving problems has been great for finding workarounds to problems. We've had cases in 3.13 where you'd go to download the FPGA and it would just crash, and we didn't know why. And students figured out, well, if you delete the Eclipse workspace and rebuild it, then it fixes that problem. And it's like, oh great, you figure that out from talking to one another. So that kind of stuff is fine, but obviously you can't copy code or designs from one another or download it from the internet, obviously. And there's always the chance that there'll be solutions available online. Just obviously don't do it. Let's see, section 14 is lecture and lab attendance policy. I don't really have an attendance policy, and I post all the lectures on YouTube. Obviously, sometimes I have cases where I lose a lecture because my voice recorder battery died, or my SD card filled on me, or I lose the recording for whatever reason. But I try to post everything on YouTube, so if you miss a lecture, you can go back, or even if you come to the lecture, you can review it. In all my past semesters, and I'm not changing this class much from when I taught it last spring, so if you can actually go back and watch the 3.17 videos on YouTube, and you can kind of preview what's coming up. But just keep in mind that the projects in this class typically are going to take longer than the time that's allotted in the lab, especially since I have to take half our meetings to lecture, right? So you will have to come to the lab outside of class to work, and you can't really do it at home because, the first project you can, but the second, third, and fourth projects, you have to be here because you have to have access to the hardware. And the FPGA boards have to stay in here because they're getting increasingly difficult to get, like everything else. So we've got to keep those in here. So you will have to spend some time in this lab, unfortunately. So just keep that in mind. We are working in groups of 2. Last spring, we had a small class like this one, and I decided to not do groups, and it didn't work out so well. It seems like everyone kind of prefers to work in groups and share the workload. So I'm just going to go back to that. If you really want to work alone, let me know. You're more than welcome to. We have enough resources, I believe, to have some groups of 1. but you'll be expected to do the same, you'll be evaluated on the same standards as the groups of 2. And the groups of 2 will both receive the same grade for all the labs. And obviously you're never going to get perfect equally contribution from both members, so I'm sure you guys know that by now, right? So just keep that in mind and be realistic about your expectations. But only 41.5% of the grade is the group projects. A lion's share of your grade is going to be individual scores, and that's the reason I did it that way, because there was a time when I just, like in 611, where 100% of the grade was group projects, and then we had students that would be in a group and they'd do nothing and they'd wind up with an A, right? So obviously, as time has gone on, I have skewed the grade more and more towards individual exams and quiz grades. So let's see. Okay, 16, project submissions. So there's a lot of information in this section. And we've had to, our policies on lab submissions has evolved over the years as we've run into problems. So number one, your projects have to, so let me just preface this by saying it's very difficult to grade these projects. We have rubrics, we do it based on rubrics, but basically in industry, you design something and it either works or not, generally speaking, right? And so it's really hard to assign partial credit, especially in a case like this where you're doing software and hardware and they have to work together perfectly, and if they don't, it's sometimes very difficult to figure out why and how close you got it to working, right? So grading is difficult. We do the best we can. We've tried different approaches over the years. Right now we're doing most of our grading based on demos, which is good because you get some practice with your communication and presenting your work. In the past, we've tried to do lab reports, but that was a disaster because we found out no one knows how to write a lab report. That may be different now that we added Electrical 201 to the curriculum, but back in the day when we tried that, it didn't work out so well. We've also tried to do auto grading. So I had a really good student for a while that developed this infrastructure to auto grade stuff. It was like an AI grading thing, but it was a little too harsh, and it wouldn't recognize corner cases, and it would assign a 0 because student would turn everything in and everything worked perfect, but it was one cycle off and 0, because it was a cold calculated machine. So we can't do auto grading. I used to have some grad students from China who are willing to just run everything on their desktop in the lab and spend all night doing that, but grad students not willing to do that anymore. So basically, grading, it's got to work. It's got to compile at least to get any credit, and then we're going to basically base most of the grade on mostly on group demos. You're going to explain to us, show us it working, and if it doesn't work, then you'll show us your code and explain to us why you think it doesn't work, right? And we're going to try to match that with a set of rubrics, which is just a check-off list of things we're looking for and assign the grade based on that. But it's not perfect. So just keep that in mind. I'm sure you guys know that from past group projects. But yeah, it's great. Students like hands-on work and they like building stuff, but grading that stuff is basically an unsolvable problem. It's impossible to fairly grade those kind of projects. Okay, only one member of each project needs to submit. So we have you submit the project through Dropbox. You have to submit it by the due date or you'll get a late penalty. So we base the late penalty on when you submit it. But when you submit it, that gives us a copy of your project that we can run against MOS or whatever we want to do and check for cheating and have a record of it. And then you demo it. You don't have to demo it by the due date. You just have to demo it at some point after you submit it, but you won't get a grade until you demo it. So generally speaking, you're going to try to demo it right after you submit it, but because we're going to be answering questions and stuff, it may be a week between your submission and your demo. And that's okay. It'll take more time to get your grade, but we'll lock in, your submission based on when you finished it is when you upload it, right? And we expect, of course, that you're not going to change it after you upload it. Now we can't, there's no way to guarantee that. We could have you physically download your submission from Moodle and then put it on the FPGA and demo that version, but I don't want to deal with that. So we're on the honor system here. You submit it, don't touch it after you submit it, then you demo it. After you demo it, we'll give you your grade. If you submit it late, that's fine. We have a late policy here, which is only 5% grade penalty per school day after the due date, and it's capped at 30%. So if you wait till finals week to submit everything, you'll lose 30% on each project, right? And that's multiplied against the score you receive. So if you get a 90%, then we'd be multiplying that 90 by 0.7 to calculate the final score, right? If you turn it in during finals week, okay? So the reason we have that policy is because we want you to be able to be confident. We want you to submit good work, even if it takes you a little longer. There's always unexpected problems, especially when you're actually building real hardware, right? So don't panic if it's late. It's a pretty easy, and that's per school day too. So we're not counting holidays and weekends, right? So one of the things about this is that a lot of times we'll say, well, it's due on Friday at midnight, and it's like, okay, but if you don't count Saturday and Sunday as on the late penalty, then technically you could turn it in on Sunday night, even though it was due Friday, and not have any late penalty, right? That's fine. Yeah, so keep that in mind. If we have a project due on Friday, you could turn it in on Sunday night, right? Because we don't include the non-school days. And so all that's hopefully described in there clear enough. You can only submit one version of any project. We've had students try to game that late policy. They say, well, I can turn it in on time and get a 90%, or I can turn it in one day late and get up to a 95. So I'll just turn it in both and see which, take the higher of the two. No, just one. We can't grade that many, so just, obviously turn in one. And that actually doesn't really apply that much anyway if we're doing demos. And you have to turn in everything by, actually I think we set the deadline not during finals week, but right before finals week, so December 8th. So you have to turn everything in by 11:59 p.m. on December 8th, which I believe is the last day of the semester before finals week. I did that for the TA's benefit. They don't like grading stuff during finals week. Okay, so you could wait all the way till the end of the semester and turn everything if you want. And some students do that because they prioritize their other courses. But obviously it's not ideal. Okay, and that's it. Any questions about that? Okay, great. So obviously you're going to want to pick a lab partner here soon. Normally I'll lecture on Tuesday, and we'll work in the lab on Thursday. But at the beginning of the semester, I'll probably have the first 3 or 4 classes. I'll just lecture until we start, until I've covered enough where you can start working on lab 1. Okay. But yeah, normally, and I'll post this on Moodle. I'll have a schedule. So you can check Moodle, and if I'm assuming I keep up on it, you'll be able to go into Moodle and you'll know whether I'm going to lecture or just give you time to work and be here to answer questions. Does that make sense? Because like I said, I don't like lecturing in this room, but we don't have a choice. But it does give us more flexibility, because if I want to do an extra lecture or we want to have an extra lab session, we have that option to do that. So in a way it's good, but it's also bad because it's just not an ideal lecturing environment. Okay, all right, let's go ahead and get into the material. Oh yeah, here's this is a copy, this is the Moodle site. Yeah, so here's the schedule, the syllabus is on here, and there'll be files that we'll be posting on there, data sheets and documentation. I'll also have links to each lecture video and each lab and each quiz. Generally there'll be one quiz a week or so. So if you look at the schedule, you just click on the quiz, you have a week to take it. You could click on the lab to see what lab we're working on, and then the submission link for the labs will be available. Everything will be in this table. It'll all be consolidated in one spot. Your grades will also be posted on Moodle as well. There's Angela, she's the TA.
Oh, guys, you will suffer me this semester.
Okay. All right, so as I mentioned, this class is about computer system design and basically building standalone computer systems essentially from scratch. So I already mentioned this in the syllabus, but I've got the topics here kind of split into three different topics, 3 different areas. Hardware design, which will cover system Verilog and FPGAs. So this gives us the ability to design some hardware and some software, and the only way to do that is with an FPGA, unless you're going to, get stuff fabricated. FPGAs, as you guys know, you've taken 611. It's an electronically reprogrammable chip. And then we're going to talk a lot about interfacing, because these standalone embedded systems, they rely a lot on components communicating with one another. And you guys haven't had that topic in any of your previous classes. Some computer engineering programs have a whole class on interfacing. That's what they had when I was at the University of Pittsburgh. But we're going to spend about a third or so of this semester talking about it. It's an important topic. And then as I mentioned, we'll talk about control, because this class focuses on not just embedded systems, which are standalone systems, but cyber-physical systems, which are computers that can control the outside world, the physical world in some way. And so under that category, we have real-time systems, which deals with software performance. You have to worry about software performance if you're trying to control the real world. So you start to get into high-performance computing and tuning software and timing software and working against time constraints, right? So that's real-time systems. And then control theory is just the practice of how to design controllers, how to design effective controllers to control a plant, which is some physical object outside the computer that you're trying to bend to your will with the software, right? So, just to kind of reiterate that, in most of your classes dealt with just programming normal computers, desktop, laptops, and servers. In this class, we're talking about, that's why I don't lecture. That's why I don't like lecturing. In here, I'm always stepping on stuff. Thank you. At least there isn't 20 robots here that I'm walking among. An embedded system, you guys took embedded systems, so you remember that an embedded system is a computer that basically just fulfills one or a few purposes. It's designed specifically to do a specific task. And a cyber-physical system is an embedded system that links sensing, computation, and control. So you have sensors of some kind which serve as the inputs, and then you have actuators that are, you have outputs that are connected to actuators. And so this is why we focus on interfacing so much in this class, because obviously the sensors have to get into the CPU. The sensors have to send information into the CPU through some means. And so how does that work? You guys never had to deal with that before, except maybe in 313 a little bit, right? So how do you do input into a CPU from a device? And then, of course, the actuators are connected to outputs. So you have to write software that sends outputs to an actuator. And so this forms like a loop that you can use to control things externally. So examples, there's tons and tons of examples of this, but obviously a self-driving car is an example of this. Satellite or any kind of autonomous vehicle or drone navigation, they have this control loop that they have to go through. And of course, the system has to be, the processor and the software have to be performant and robust enough in order to actually fulfill the requirements of the control loop and controlling these things. Same thing for, like thermostats and weather stations and cameras and all that kind of stuff. These are all systems, cyber-physical systems, and they're specifically designed for that purpose. So in all of these cases, they kind of had to start from scratch and build a standalone computer to do that, right? They couldn't you don't buy something off the shelf. So we're going to talk a lot about constraints. Constraints are requirements or limits or they're minimums or maximums that you have to adhere to when you design the system. So examples of this would be like power envelope, where it's like you got to buy a processor, but it can't use more power than you can give it in whatever system you have. And this is true even like, you think like in a Tesla, you're like, well, if it's in a car, there should be plenty of power. You get the power from the alternator. You get like a kilowatt, It's like, yeah, but you got enough GPUs in that Tesla, it's going to use more power than the alternator can provide, or the batteries or whatever can provide. So you're always working, anytime you're in a mobile type environment, you're working within these power envelope. And then, of course, performance, as I mentioned. If the processor is making some calculation in order to make a decision about what to do next or how to actuate the system next, you better be able to make that decision before the physical world gets ahead of you, basically. It's kind of like the system has to be able to stay on top of it and complete its calculations on time. So there's always some kind of a performance requirement anytime you design one of these cyber-physical systems. And then interconnectivity, you might buy a processor and it may not have enough I/O channels to connect all the sensors that you need. So you may have to multiplex some or come up with innovative ways to solve that. And then for obviously battery storage, you want to try to make, if you're on a battery, you want that battery to last as long as possible. So these are all constraints. And then you have optimization goals, which are things that give you a competitive advantage over other companies building the same thing. Things that make your product look better. So for example, you might meet all the design constraints, but you might have a better solution, a more effective system. It might be faster, the battery might last longer, it may be more responsive. So these are optimization goals, and every time you design one of these things, you're always trying to work within constraints, you're always trying to maximize your optimization goals, and usually there's some kind of a trade-off where you're trading off one thing for another, right? You can't have everything. And in some cases, the trade-offs are inherent in the hardware technology itself. Okay, so here's, for example, a bunch of embedded systems I picked, and I put them on this spectrum where on the left side you have a smaller power, less power it takes to run it, but less performance. So you have this trade-off between power and performance generally. If you want more power, if you want more performance, you're going to have to you're going to take more electrical power, right? So for example, like if you pick up an electronic greeting card at the drugstore, and you open it and it plays some song, there's actually an Atmel processor in there that powers that thing. But the idea is that, you want to be able to let that card obviously, you want it to work for as long as possible, right? And so that processor is going to be like 1 to 10 milliwatt processor, but at the same time, it's only get about 1 to 10 million instructions per second in terms of its performance. But you don't need that much performance because the only thing it needs to do is play a song, right? But technically, it could run any program. It's Turing complete, so you could run a nuclear explosion simulation on that processor in theory, but really for its task, you just need it to play the song, right? And then as you work your way up, you get into, like, for example, an Apple Watch is up here around the 10 to 100 milliwatts. And it's going to get about 10 to 100 million instructions per second performance. And then you get all the way up into, like, for example, I think probably the Tesla would be, about a 100-watt processor in there that's going to give you about 100 billion instructions per second, because that's what you need to do all the machine learning stuff they have in there. So you have this trade-off. Another example of this that I like is this idea between, if you look at different processors from like a supercomputer all the way down to an Arduino. This is the Arduino that we used to use in this class before we switched to the FPGA. The Summit supercomputer, I don't know if it still is, but at one time it was the fastest computer in the world. It had 2.4 million processor cores and 3 petabytes of RAM, and it was 200 petaflop machine. They're trying to get up to 1,000 petaflops is the new objective. But for a while, the 200 petaflops per second, and flop is a floating point instruction, so 200 quadrillion floating point operations per second, uses 10 megawatts, and basically it has this power efficiency of 20 gigaflops per second per watt, right? Is what the efficiency of that is. You get down to the Arduino, and the Arduino is an 8-bit CPU, and it uses about 20 milliwatts of power, right? So your instinct might be like, well, that's really power efficient, an Arduino. I mean, it uses 20 milliwatts. How can it not be, right? Well, the problem with the Arduino is that it only got about 200 kiloflops per second in terms of floating point performance. So if you take its floating point performance and divide it by its power usage, it's only getting about 10 megaflops per second per watt, compared to the supercomputer that's 20 gigaflops per second per watt. So what that means is that even though it's totally counterintuitive, the supercomputer is thousands of times more power efficient than an Arduino in terms of its computational efficiency, how many joules per op that it gets, which is what this metric breaks down into. Number of joules of energy per operation, computational operation, is about 20,000 times higher for the supercomputer than it is for the Arduino. And that's totally counterintuitive, right? Because you don't think of a 10 megawatt computer as being power efficient, but it turns out it is, because you get economies of scale here. Because this thing is so massive, it uses a lot of power, yes, 10 megawatts, but it also makes it hugely efficient because just the scale that you're at. It turns out that whenever you have a processor that's a very small scale processor, a very low power, it's also hugely inefficient, just because that's the nature of the technology. You can't make a super efficient but also low power processor. It doesn't exist. It's just not possible. And then the Raspberry Pi is right in the middle. So the Raspberry Pi is a 15-watt processor, and it gets about 1.8 gigaflops per second per watt, because it gets about 27 gigaflops per second of floating point performance and uses 15 watts, right? So that's, to me, I like this example because it shows that it's a huge challenge to make efficient and also low power processors. I mean, if you can get the same efficiency as Summit on your phone would last, 3 years, right? If you can achieve the same level of efficiency as the supercomputer. Okay, so that's just kind of my introduction. So I want to start talking about hardware-software interfacing a little bit. So some of this stuff we covered in 313, although I haven't taught 313 for a while, so I'm not sure how it's being presented now. Although it's Rasha's. Did you guys have Rasha? Okay, Rasha was my former student. She used to TA the class, so I think she probably taught it like I did. But hardware-software interfacing is probably not something that you guys ever cover, aside from 313. And the reason is because whenever you write code for a computer, it's all handled for you by the operating system. You don't have to worry about it. You just print something and it shows up on the screen. You're like, well, how'd that happen? And then, unclear, And then you take 212, and in 212 you learn about processors, and you say, well, there's a processor and it has an instruction set, right? You got all these instructions. You got loads and store instructions, load and stores, you got arithmetic instructions, and you got branch instructions, but where's the I/O instructions? How does it talk to the outside world? Unclear. That's the missing piece of it. It's like, okay, I get it. I can write a program in MIPS assembly, and I can have it do stuff, but where's the part where it actually prints to a screen or a printer or a network card or a GPU? Where's that happening? Unclear. It's a secret, right? Well, it turns out the answer is there's only 3 ways that the CPUs can talk to the outside world. There's only 3 mechanisms, and these are the same 3 mechanisms that were in place in 1955. There's programmed I/O, interrupts, and direct memory access. That's the only way the software can get messages outside the confines of the ceramic package that are the CPU. So programmed I/O is done through load and store instructions. So the idea is that the program issues load and store instructions, but to special addresses. Those special addresses are called I/O addresses, and they bypass the memory and they go straight to a peripheral, an I/O device. That peripheral can be outside the physical CPU, or they can be on chip. Like, they could be outside the CPU but still within the chip, like is in the case of a system on chip design, or they could actually travel outside the CPU. Like you could do a programmed I/O and it'll literally come outside the Intel CPU across the quick path interconnect all the way across the PCI bus and down to your network adapter with one store instruction, right? That's possible, right? So the problem is, and you might say, well, then why haven't we ever done that before? Well, normally, if you have an operating system, only the operating system's allowed to do that. You're not allowed to do that. If you try to do that as a user, you get a seg fault, right? Because that's a privileged instruction, right? So unless you're writing an operating system driver, you never get the experience of doing programmed I/O, and thus you never get to do software-hardware interfacing at all, which kind of sucks, because that's a fundamental concept in computing. You have to be able to get information outside the CPU from the software to the hardware. So in this class, like in 313 and in 611, we're not using an operating system though. We're doing what's called bare metal programming, which is where you essentially just write code that runs on the metal and you don't have an operating system. And in fact, a lot of embedded systems are designed that way. Because an operating system is great, it makes things easy, and you can time multiplex the CPU very easily with that, and you can provide a lot of services to the software and make the software more productive so you don't have to worry about these low-level details. But it also makes the performance non-deterministic. An operating system is always doing stuff. It's always taking control away from software and giving the control of the CPU to some other piece of software, or to some server, or to some interrupt. You never know what it's doing, right? So if you're writing something that says, well, I'm a cruise control system for a car, I got to adjust the power that the engine is putting out, and I got 10 milliseconds to do it. If I don't do it in 10 milliseconds, I'm going to speed up beyond what the driver set as the speed, right? Linux will not guarantee that anything can be done in 10 milliseconds. There is no way in any operating system, unless you have a real-time operating system, which are still to this day very obscure, expensive, and hard to use. Any normal operating system gives no guarantees at all about a deadline or a limit how long something has to run. There's just no way to specify that. You can't tell Linux, hey, I got a simple task, should be not a problem, but I gotta have it done in 10 milliseconds. It's like, Linux is like, nope, I'll get it done whenever I get it done, and you'll have to accept that, right? That's the problem. So the question is, do you use Linux on a cruise control system? No. No one would do that. That's insane. You know, you would write software either with a specialized real-time operating system, which, by the way, are not operating systems as you know it. Real-time operating systems are like libraries, much the same way the BSP worked when you took 3.13. That BSP that you had that had some routines in it that eased the interfacing with the hardware, that's essentially what a real-time operating system is a BSP. It's just a hardware abstraction layer, set of libraries. It's not something that gives you a shell prompt. There's no shell prompt. There's no interactivity with a terminal with a real-time operating system. You essentially statically compile your code into it, and then it just acts as a runtime environment that manages the execution. But it doesn't give you a bash prompt, right? So if you ever see a prompt on an operating system, it's not a real-time operating system. Okay, so anyway, in this class, since we're focusing on cyber-physical systems, you will now have the opportunity to work without an operating system and do direct software-hardware interfacing. So if you ever have to write a driver, or if you're ever designing a system like this, you'll have that experience. And then, of course, now programmed I/O, by the way, is a way. You know, I'm sure you guys remember this, but programmed I/O is a way for the CPU to act as a master and either send a number out, a value out to hardware, or to explicitly read a number from hardware, right? But the CPU has to initiate that process, right? The problem is what if the hardware, the peripheral, wants to do something? It wants the CPU to service it, right? As opposed to it servicing the CPU. What if you have a peripheral that demands the CPU's attention? That's done through an interrupt. So an interrupt is only initiated by a peripheral, by a hardware component, and it's basically a wire that goes back to the CPU that tells the CPU that someone needs the CPU's attention. CPU can ignore it if it wants, or if it wants to service that interrupt, it can do so, at which point it has to then use programmed I/O to say, what's up? What do you need? You know, so it does a load instruction to an I/O address that corresponds to that interrupt and says, what do you need, buddy? I saw your interrupt. What's going on? You got a packet? Got a packet for me? What's going on? So that's basically how interrupts work. And then direct memory access is the way that you do high-speed I/O. So programmed I/O is horribly slow because you can only do one scalar at a time. If you do a load or store instruction, it's one 32-bit value or one 64-bit value, right? That's it. What if you want to transfer a block of data, like if you're reading from a hard drive? You want to be able to send a whole big block of data, a big old block, right? How do you do that? Then you use direct memory access, which is another peripheral in and of itself that you talk to through programmed I/O and interrupts. But when you talk to it, you tell it to transfer a block of data from a peripheral directly into memory without the CPU being involved. And that's the way that you get like video cards, network adapters, and hard drives. Basically, you have this external thing that takes care of moving blocks of data without the CPU having to be involved. Because if the CPU is involved, it slows down the process because it's an intermediary. The CPU has to say, okay, take something from here and put it in there, take something from here, put it there. It's too slow, right? Whereas the DMA controller speeds that process up. But these are the only three ways that software and hardware talk. And like I said, it's always been the case. There's been no advancements in this area for 50 years. This is how everything still operates. So that's from a software perspective, obviously. From a hardware perspective, if I'm designing hardware, now I can just talk. I have wires. I could flip wires, right? And I can communicate through wire flipping, through driving wires with gates or drivers or amplifiers or whatever. But that process is governed by an I/O interface of some kind. And there's a whole bunch of those, right? For example, the Intel QPI is the one Intel uses. AMD has Rapid I/O. They're both fairly equivalent. They're a high-speed asynchronous serial interface. DDR5, you might have heard of that. You might say, well, that's memory, right? Well, no, that's actually a protocol that you use to communicate with the type of memory, DDR5. SATA, which is the old-fashioned hardware, serial ATA, right? Hard drive, rather. PCI Express, you've all heard of that. That's a high-speed serial interface, differential signals. USB, everyone's familiar with that. And then SPI is the one that we'll cover in class. These ones are very complex. So we're not covering these. We're going to cover some of the simpler ones like SPI, I2C, and UART because those are simple. They're easy to wrap your head around, and they're also still very commonly used in lightweight embedded systems like Arduinos and stuff that that you're going to have at the Maker Faire, right? Whereas this stuff, if you're doing PCI Express, you're at a big company. You're not doing Maker stuff. That's wildly complex. I have a book on PCI. It's this thick. Okay, so, and even USB, you might say, well, come on, USB, man, it's been around since 1991. Yeah, it's a packet-based network protocol that's wildly complex. So we can't even cover USB. I thought about it, but it's essentially a network protocol more than it is just a hardware communication protocol. So we're going to cover some basic hardware protocols, but the advantage there is that, to do that, you have to learn how to read timing diagrams, and you get some experience with handshaking and the types of tricks that are used for those protocols. Okay, so let's talk about programmed I/O a bit, because we're going to be using this. I mentioned that the CPU basically just uses loads and store instructions to specific I/O addresses. And again, if you use those I/O addresses in Linux, it'll just crash. It'll say, yeah, you don't have access. It'll give a seg fault. Or actually, you can't even actually, technically you can't even access I/O addresses in a Linux program because you have a virtual address system in your user code. So like these are physical, the I/O addresses are physical addresses. These are physical addresses that exist outside of the virtual memory system, outside of the page table that Linux has, right? So you have to be, if you have an operating system like Linux, you can do this as long as you write a kernel driver, kernel module, you can do this. Or if you have no operating system, then you would do this and package you'd probably write a little routine in your hardware abstraction layer to do this, and then you can still provide kind of a simplified interface to the user. But anyway, you've got these address ranges, and so you might have a CPU, and that CPU is going to be inside of a system on chip, and it's going to be connected to peripherals through some kind of an on-chip interconnect or a network on chip of some kind. Now on an FPGA, that is called AXI. It's the AXI bus. And all the embedded systems have adopted that. It was a standard that ARM came up with about 30 years ago. And for whatever reason, it kind of just emerged as kind of the standard. IBM had one called Core Connect that Altera FPGAs, Xilinx FPGAs used to use that, but they got rid of it in favor of AXI. And there's another one on Intel FPGAs called Avalon, which you can still use, but they're even replacing that with AXI, right? So this is basically an on-chip network. But basically all it does is it allows you to build an interconnect, which is where the CPU has one memory interface. It only has one interface that has an address, data, and read or write control lines. But somehow you have to broadcast that out to all your peripherals, and that broadcast is performed through this interconnect. And the interconnect is built with a certain on-chip network technology in mind, like AXI, right? And so what happens is when the network issues a load or store to an I/O address, that interconnect knows what the mapping is between your addresses and those peripherals, and it uses the address as kind of a destination field. It uses the memory address as an IP address, basically, if you think of it as a network. So the CPU gives it a memory address, and this guy interprets that as an actual address of which peripheral, because it knows that mapping, the I/O mapping, and then it uses that to route the load or store to the appropriate peripheral. So you may have, for example, a USB peripheral, a USB interface that allows you to go off chip to USB, or an SPI peripheral, or a timer peripheral, which doesn't go off chip, but it has a real-time clock in it that you use to synchronize everything. Or a UART peripheral, or you could even have like a digital to analog converter peripheral, or a pulse width modulator peripheral. These are all peripherals that are available on the chip, and they're all addressed by their special memory address from the CPU, ultimately through load and store instructions. And so as I mentioned, you just do load or store, and then if you're loading, meaning that I'm requesting a word, I'm requesting data from a peripheral, that's usually referred to as a control word, control register. Scratch that, status register. If you read it, it's a status register. If you write it, it's a control register. But that terminology is a little antiquated. Not many people, not everyone still uses that. And in fact, a lot of these registers you can read or write. They're read or write. So you can treat it like a status or a control register, but that's just a terminology thing. Okay, so each one of these guys is going to have a range of addresses that corresponds to how I address that with my load or store instruction. So for example, the USB I have listed here has an address range of 100 in hex to 1FF in hex. So the question I might ask, like on the quiz, is what is the size of the memory space? What is the size of the space of addresses that I can store to that will go to the USB, that will be routed to the USB through the interconnect? And the answer is going to be the last address, 1FF, minus the first address, which is 100, and then you have to add 1 because it's an inclusive range, right? So it's basically 1FF minus 100 plus 1, and this is in hex. And the answer is 100 in hex, or 256 in decimal. So it has a 256 byte range that maps. That's the amount of the memory space range that maps to that guy. And every peripheral will have a different space depending on how many control and status registers it has, right? Some of them are pretty small. Some of them may just have 16 bytes. But other ones may be, much larger, right? So it just depends on what the needs of the peripheral are. Now in Linux, by the way, if you ever get into like compiling Linux kernels, Linux has something called a device tree that keeps track of these addresses. And it's something that's compiled alongside the kernel. So when you launch the kernel, the device tree, which is a special file that you write it in text, but then it gets compiled into a binary form, and the binary form is what reads when you boot Linux. It just has all the ranges in here. So like for example, if you wanted to build an FPGA platform like in 3.13, but then you wanted to run Linux on it, then you would have to create a custom device tree that would have all of these address mappings stored in there, so Linux would know, so Linux drivers would know how to connect to those guys, right? And that's all communicated through the device tree. In this class, we're just going to treat them as hard-coded, as my former student Charles would say, we're going to treat them as magic numbers, right? Like hard-coded values that we put in there. Okay, so then these control and status registers are often split up into bit ranges, because a lot of the signals that you want to send to hardware or receive from hardware might just be 1 bit or a few bits. And so generally what they'll do is they'll pack these bit fields into these control and status registers. And so when you access them from software, you have to extract the bits you want or insert the bits you want, right? So you have to do bit manipulation. The problem is that every instruction set architecture I've ever seen doesn't work that way. You can only write words, right? You have a processor, you can load an immediate, which is a word, it loads a whole register. Everything is registers, right? So if it's 64-bit processor, you're dealing with 64-bit values. There's no way to put a bit into a value, right? At least not in one instruction. You have to use multiple instructions, and you have to use tricks to do bit manipulation. So for example, this is a register, a control register, and when you read the data sheet, it'll show what the ranges of bits are and what their purpose is. So for example, this is an 8-bit one. And by the way, a lot of depending on the processor, you may have a 32-bit registers or 64-bit registers. This one's 8-bit because this example was derived with the Arduino in mind, the 8-bit Arduino, and it uses 8-bit control and status registers. So this thing's only 8 bits, so the bits are numbered from 7 down to 0, from left to right, most significant to least significant, and then it's broken down by field, and each field has a name. So for example, bits 5 down to 3 is temp. It's a 3-bit code that indicates the temperature, the current temperature of that peripheral. So generally, if I want to read the temperature, I would load that control register into one of my general purpose registers. Now you might say, whoa, hold on, are we writing this in assembly language or what's up? No, well, no, you would into a C variable, right? You'd load that into a C variable, which ultimately would be in a register, but you don't necessarily write it that way because you generally write in C with embedded systems. You load that into a C, 8-bit C variable, and then your goal is to then take those 3 bits out and interpret that as the temperature. So you got to extract those 3 bits and you got to knock off all the other bits. You got to get those 3 bits out, and you have to delete the other 5 bits. Right? So how do you do that? You guys have any idea? You ever had to do that before?
You read it, and then you and the most significant bits.
Yeah. Well, that'll isolate those bits. You can bit mask and isolate, but then they're going to be in the middle of the. You don't necessarily want them to be in the middle. You may want to also. You want to use them, yeah. So you could leave them in the middle, but a lot of times you might want to not only to isolate them, but shift so they're positioned down in the least significant bits. So you could interpret it as a value from 0 to 7, for instance, as opposed to a weird value that's been multiplied by 8, right? Essentially, right? So that's essentially, yeah. So he's right. That's basically the way it's done. Is you have to use a combination of bitwise logical instructions, operations, and shift operations, which is why we have those, right? Now you might have been wondering, like when you took 212, there's this huge emphasis on shift instructions and bitwise logical instructions. You're like, I never use these in 145 and 146 and 240 and never used them, right? Even in robotics, we never use these things. Why is there such an emphasis? Why are there so many instructions for these little operations that we've never used? It's all for this bit. It's all for bit manipulation. Like whenever you have to manipulate bits within a register, you need to do that. So that's what they're there for. So for example, how would I set? Now here's an example of not reading, but this is actually setting. What if I have a value? So I have a variable that's called val in my C code, and I want to set bit 2 to the value 1, right? Now if it's already 1, don't do anything, obviously, but let's assume that it might not be 1, it might be 0. I want to set that 0 to 1, but I don't want to mess with any of the other bits, right? Because, see, the thing is that with hardware, you would read a control register out of the hardware, and then you may have to put some bits in a field, but if you screw up the other bits in that register, you can cause side effects, right? So a lot of times you just want to change individual bits or individual ranges of bits. So in this case, I want to set bit 2 to the value 1. So I'm assuming that I've got val, I've already read it. It's in my register file, it's in my C variable. What do I do? So there's actually a lot of ways to do this. One way is you could take a temporary variable and set it to 1. So I just say temp equals 1. Then I can shift that temporary variable 2 bits to the left, right? Because if you set a variable to 1, it's actually setting the least significant bit, the rightmost bit. I have to move that rightmost bit into bit 2 because that's where I'm targeting. That's my target. So I move it by shifting it 2 bits to the left. So basically I'm taking a 1 bit and positioning it where I want it. And then you do a bitwise OR between the original value and that temporary value. And by doing that OR, you're going to set bit 2 to 1. Now if it was already 1, it'll stay 1. It's not an XOR, it's just an OR, right? So an OR will not affect it if it's already 1, but if it was 0, it's going to flip that bit to 1. And so basically in one line of code, the one line of code in C, and you might not have done this in C or Java, but it works, you take a constant 1 less than 2, which does basically this creates the temporary variable. It takes 1, shifts it 2 bits to the left, and then a single bar, which is a bitwise OR, with the original val. So in one line of code, you can set bit 2 to the value 1, or leave it at 1 if it was already at 1, right? Now you might say, well, wait a minute, like you're hard coding 2? Like, yeah, okay, yeah, that doesn't have to be a hard coded 2. That could be a variable. Right? That could just say bit, and then you could set that variable bit, and that would be what bit you're setting, right? It doesn't have to be hard-coded, right? That's just an example. That's just that's my crappy programming there where I had the magic numbers in there. But you can have the variables in there, right? But that's essentially, and that's only one way to do it. What if I want to set it to 0, though? That's a little bit more complicated. So if I want to set it to 0, I would start out by taking that temporary value, setting it to 1, shifting it 2 bits to the left. But now I want to set that bit to 0, and again, leave it at 0 if it's already 0. So how is that going to work? Well, you have to pretty much do a bitwise complement. So you take the 1, you put it into its position 2, and then you flip all the bits. So all the 0s become 1, all the 1s become 0, right? So now what you end up with is a 1 in every bit position except for bit 2. Right? And then instead of doing an OR, a bitwise OR, you do a bitwise AND, right? Which basically masks off all the bits, or masks off bit 2 and leaves all the other bits unaffected. And that way, we can guarantee that after doing this, bit 2 will be set to 0. And again, remember, bit 2 is counting from the right side starting at 0. So 0, 1, 2, right? So bit 2 is off on the right-hand side. The third bit from the right is bit 2. And so the code to do that in C would just be val equals val, ampersand, which is a bitwise and, tilde, which is a bitwise complement, 1 less than 2, right? And yeah, and so that'll do it in one line of code, or you can split into multiple lines. Okay, how about isolating one bit? We already talked about this. If I just want to read bit 3, okay, so I could take value, assuming I have the value, the whole register in value, I want to extract bit 3. So to do that, I can take value and shift it 3 bits to the right, which would position, basically that positions bit 3 on the right-hand side into bit 0 by shifting it to the right. Now remember, before we shifted to the left, now we're shifting to the right. I want to take that bit I want to read, because I'm reading, not writing. I want to bring it from bit 3 down to bit 0. And you might say, well, why do you want it in bit 0? Well, because it should be right justified, right? And also, by doing that, I can just do a bitwise AND with the value 1, and it will isolate that specific bit, right? So basically, shift 3 bits to the right, and with 1, and that'll just leave me with 1 bit, whatever the original bit 3 was, all by itself in the register and all the way to the right-hand side, so it will be properly aligned in the value, right? Yes?
Well, I just want to let you know that those examples are not hard-coded. Like, you can have other approaches in your labs. For example, in this example, you could shift 3 bits to the left, and then, or with the value, and then shift it back if you need it in the first position. So you can use those examples on the slides, but don't get afraid if you don't have slides. You just can come up with your solution, and if that works, that's fine.
Yeah, there's other ways to do it. And also, if you look at the lecture, the textbook that I'll post, I have some other ways to do it too in the actual text. These are just one example, one possible way to do it. Okay, another option is if you don't want to shift it, you could just take a 1, shift it 3 bits to the left, and then just AND with that, and that will isolate that bit. It just won't right justify it. So that's another option. Sometimes that's all you need, because if that 1 bit is a flag, all you care about is whether the result is a 0 or non-zero value. So if you're going to use this in an if statement after this, then you may not care about right justifying that bit. How about multiple bits? What if we have bits 5 down to 3 and we want to extract those out? Well, in that case, it's a little bit harder, but you would shift it right by 3, right? Because it's 5 down to 3. So you take the second number, which is the right boundary of the bit field, right? The right boundary, the least significant boundary, and you'd shift it right by 3 bits. So that would position the original bits 5 down to 3 would now become 5 minus 3 down to 3 minus 3. So this would make it 2 down to 0, right? So if it was bits 5 down to 3, I shifted 3 bits to the right. Now it's in bits 2 down to 0. The problem, though, is I still got garbage in there, because I do have bits 2 down to 0 in position here, but I have bits, the original bit 7 and the original bit 6 is now in bits 4 down to 3. I don't want those guys. I want to get rid of those. So again, you could bit mask, but now instead of bit masking by 1, I have to bit mask by 111, right? Which is hex value 7, right? Another way to do that, though, is to say, okay, I want 3 bits. I want to mask off all but the least significant 3 bits. So you could take the value 1, shift it 3 bits to the left, and then subtract 1, right? That seems complicated, but basically, if I take 1 and I shift it 3 bits to the left, that's going to give me an 8. And if I subtract 1, I get 7, and 7 is 111, right? So basically, if you want to set n bits to 1, right, you just say 1 shifted by n to the left and subtract 1, and that will always give you n bits set on the right-hand side. So this will extract, like, for example, the temperature field that I was talking about earlier, right? Okay, so here's a summary. Here's a summary of those things. So if I want to set a bit to 1, if I want to set a bit to 0, if I want to isolate, extract, read, isolate / extract / read bits n down to m, right, then you can use that line of code where I've got it now with variables in there. Now, be a little careful here because I don't know if you noticed this, but I have parentheses around certain things, but not other things, right? So I don't have parentheses around n minus m plus 1, no parentheses. But yet, for some reason, I have parentheses around 1 shifted by n minus m plus 1, right? And why is that? Well, that was actually deliberate, and you can fall into a trap with this because usually you would assume, well, you might assume some order of operations, but you should double check what the actual order of operations are just to make sure what you have to put, because you don't want to say 1 shifted by n minus m plus 1. What might end up happening is it may end up shifting 1 by n and then subtracting m and adding 1, right? The assumption here is that I want the shift amount to be n minus m plus 1 and shift by that. So you have to be careful that you group these things according to the order, the operator precedence. So why did I do this? Well, it turns out that add and subtract have higher precedence than shift. So when I do this, it is going to do the add and subtract stuff here first before it does the shift. The problem is that the shift has higher precedence than the logical operations, which is strange. I wouldn't have designed it that way. That's kind of dumb, I think. But that's how they did it. So I have to make sure that I do my shifts and then I do my ampersand here. Yes?
Exactly.
What's that?
Exactly.
If it works, then you can start removing parentheses and cleaners.
Well, basically what he says, and that is how I do things usually. Well, you have 2 ways to go. You can remember all the big table of operator precedence, keep it in your mind.
No, you search. You just search for C operator precedence. It's the first hit on Google.
Or you can just put, if you have smallest doubt, put parentheses. It won't hurt.
Yeah, it won't hurt if you put it. It just makes the code totally unreadable when you have too many parentheses.
Well, I will be reading your code most bits. It's my
So, it does harm the readability quite a bit if you overdo the parentheses. Another option is you could use multiple lines of code, right, to pre-calculate the shift amounts. But again, it all depends on, generally you want to try to make it readable. The other thing too is you don't want to try trial and error, because keep in mind that if you're writing this code for an embedded system, this is not 145 and 146 where you can just run an Eclipse and test it. You're writing this code, you're downloading it to an Arduino, and then you essentially get cut off from it. So Arduino has no debugger. So if you do this and it doesn't work, there's just no way to know if it works or not on the Arduino. You can try to print something to the console and do old style kindergarten print debugging, but there's no real debugger on Arduino, right? So you have to be a little bit more careful when you write embedded code, because you don't have the luxuries you do of writing code on a PC. Yeah, or an FPGA, same idea though. FPGA does have a debugger, but you guys know from 3.13 how responsive that debugger is. You hit the F10 button to step to the next line, and you wait about 20 seconds for it to actually happen. Why does it take that long? I have no idea. It's USB. Yeah, USB's pretty fast though, buddy. So I don't know. I don't know why it takes that long, but it's cumbersome. Okay, now how about loads and stores? I mentioned loading and storing. I said load and store instruction. That's how you write and read control registers. And you might be thinking, yeah, if it's assembly language, but there's no load and store in C. Correct, there is not. The way C handles loads and stores is through a star operator, indirection operator. Dereference operator, I should say, dereferencing, which looks nothing like a load or store. But, and you guys might not use pointers I think you use pointers in 240, but basically what you do is you put the address in a pointer, okay? So you have a variable that's an address, which is also known as a pointer. Then you put a star in front of it, okay? Now, depending on whether that expression is on the left-hand side of an assignment or the right side will then determine if it's a load or store instruction. So if I take an address and I stick a star in front of that address, and I put that on the right-hand side of an assignment expression in C, that will be translated to a load instruction. Likewise, if I do it and that's on the left-hand side, this is now a store instruction, right? So this is how you implement loads and stores in C. Now you have to be careful here too, though, because the problem with this is, depending on what architecture you're on, you may not want to do it this way. If you do it this way, there's a chance that instead of going out to the hardware, again, I'm assuming this address is an I/O address, right? If the address is an I/O address and you do this, it may get caught up in the cache. And you don't want to go in the cache. I/O instructions, I/O load and store instructions are supposed to bypass the cache because the cache is only for memory. These aren't memory. This is a control status register. This is a transaction I'm doing directly with hardware. It shouldn't be caught up in the cache. The cache shouldn't be a factor here. So sometimes if you have an Arduino, Arduino's fine with that. I don't think it even has a cache. It's just too primitive, right? But if you're on like the Neos processor that we use on the FPGA, it gets around the cache by having a separate load and store specifically for I/O. They have a load I/O and a store I/O instruction, okay? They're the same thing as load or store, but there's one bit set in the machine code for that, one bit that basically says bypass the cache, right? And you have to make sure that bit is on, but you don't have control of that. The compiler has control of that. So what do? Well, in that case, you have to make sure that you use intrinsics. Okay, so in the case of the FPGA, there's an intrinsic called IORD32, which looks like a function, but it's actually a macro. And that intrinsic will get translated into a load I/O instruction. So same thing as a load, same thing as just doing an indirection, a dereference here, but it gets translated to the proper machine instruction so it bypasses the cache. Unfortunately though, these intrinsics vary by vendor, they vary by CPU. So the intrinsics you'd use on Intel are different from the intrinsics you'd use on the Neos, which are different than the intrinsics you use on ARM, which are different from the intrinsics you use on a RISC-32. So you have to look this up. You have to look it up. Now Arduino just uses a plain old dereference, right? Which is why when we originally developed this course, we were developing it with Arduinos in mind. But if you're using a more sophisticated processor, you may have to use an intrinsic for these programmed I/O operations, okay? Now, generally, like I said, you guys usually don't ever see these because they're buried in the driver code, right? But if you don't have an operating system, then you have to become aware of this. So you have to look it up. Okay, let's see. Okay, so here is kind of a slide that puts everything together. So we have this thing, bit twiddling or bit manipulation. So you have this register. You would have something, for example, called a register called PNTLS. These registers are usually named with like an acronym or a shortened name. And so PNTLS would be something that you would have like in a defined PNTLS reg. Maybe that's at address 10. So that would be the I/O address of that. But I'm going to store it as a macro, so I can just use the macro name, so I don't have to put the address in my code. And if I need to change the address, I can just update it in a header file, right? And then when I access it, I would say volatile, if it's an 8-bit register, uint8_t star PLTS. So now I'm declaring this thing as a pointer, right? And then I'm just going to set it to, in this case, actually I calculate the effective address, USB address, which is the base address of the USB adapter, and then PLTS reg is just the offset, right? It's how far into the USB address space I go to get that. So it's an effective address calculation. So I calculate the effective I/O address of that specific register and declare it as a pointer and set it as a pointer. And then once it's in a pointer, I simply dereference it, assuming that's okay for this architecture. I dereference it to load that register, and then I can use bit manipulation to, for example, set the on fire field to 1, right? Or in this case, read the on fire field to check it. I'm treating this as an input, so I'm checking to see if the peripheral's on fire. In this case, on fire was also in a define because it happens to be bit 6 in there, right? So basically, it's the same thing I already showed you, except I'm using variables now, or in this case, actual defines, to set the bit field numbers and the I/O base address of the peripheral, and then how far into that address space that register is. So this is kind of a complete example where I'm reading a flag to check to see if my peripheral's on fire, and then I set the halt bit to turn off the peripheral afterwards. Right? So I check if it's on fire, and then I set it to halt. And notice here that reading a flag is where I dereference the thing, the pointer on the right-hand side of the assignment, and when I set an output, I'm dereferencing on the left-hand side of the assignment, right? So this is just, like I said, just kind of putting everything together. Any questions about that? And this is exactly how you access Arduino control registers. Now you might say, wait a minute, I've written Arduino code. I never had to do that. Yeah, because you use the baby library that came in the Arduino. You use their libraries. Their libraries doing this. But if you were writing your own library, you would have to do that. But if you use the kindergarten mode, then you probably wouldn't see that. You would just call a function that says read the fire bit, right? Okay, but that's what's happening under the hood. Okay, so let's see, how are we doing on time here? Got about 5 minutes. So I'll just go through one example question here. So write a line of C++ code that sets the value of bit 4 to the value 0 in the variable name myvar, leaving the other bits unchanged. So how would you do that? You would take myvar, and you would take 1 shifted by 4, take the bitwise complement, and do a bitwise AND. And that would just clear bit 4 and myvar, leaving the other bits alone. And if the bit 4 was already 0, then it would have no effect at all. Okay? Makes sense? That's easy, right? Okay. Now this question is a little obnoxious. But it says, consider the following snippet of code. Indicate which of the following lines of C code will cause the same value be stored in the value y. So this is an example that's basically saying find the equivalent code, right? So there's two ways to do this. So in this case, I'm taking the value of x, shifting it 4 bits to the right, taking the value x, masking off the lower 4 bits, inverting it, and then shifting that to the left by 4 bits, and then combining them together. So basically what I'm doing is I'm taking the upper half and putting it in the lower half, right? And I'm taking, this is the upper half, I'm going to put it in the lower half. And then I'm going to take the lower half, and I'm going to isolate the lower half, invert all those bits, and then put it in the upper half, and then merge everything together. Does that make sense? So which one of these lines is doing the same thing? Let's see. So this guy is going to mask off the lower 4 bits and shift it to the upper 4 bits, and then invert the whole thing. The problem with this one, though, is that when you do this, it's going to take the ones that were left behind that you shifted in and invert those bits. I don't think that one does that. No, it doesn't, because, it doesn't. So this one, I think that one would be ruled out, right? This one takes the upper 4 bits, shifts them to the lower 4 bits, takes the lower 4 bits, shifts it to the upper 4 bits, and then it does a complement, but it complements x before it does that. And I think that one's it. Yeah, I think that's the right one. Right? Makes sense? I'm going to cheat and find out. Okay, so so this one, the impact of it is the lower 4 bits gets put up in the upper 4 bits. The upper 4 bits gets put in the lower 4 bits. This one, you don't get the same effect because it's negating the original upper 4 bits. This one is the correct one here. Yeah, so I got it right. But basically the way I solved it is, you could see as I tried to make a little table that basically recorded the impact of those operations, right? Alrighty. Okay, so that's all I have for today. Any questions? Okay, well, I'll see you guys on Tuesday, and we'll just continue with the lecturing until we get to the point where we can do the first lab. Thank you.
Okay, so you want to have lecture on Tuesday, right?
Yeah.